So we started out with focusing on continuous time systems which have a single input and single output. We said that there could be systems which have discrete time signals, and they can also take multiple input and can also produce multiple output. So there are different kinds of systems. What we said was, in this course we'll focus ourselves only on systems that take in continuous time input signals and produce continuous time output signals, and they take a single input and produce a single output. We'll focus only on those kind of systems. And then we said it could have certain properties, and then we defined those properties. The first property was memory. So what memory meant, that if a system produced an output which depended on not only the present input but also the past input, such systems could have memory. Okay, and then we define what is known as causality. So what causality means is that if the present output depends only on the present input or the past input, then we say that it is a causal system. Basically, it does not produce an output which depends on future input. Okay, such systems are all causal because the current output is caused by only the current input or the previous input. And we know that all practical systems are causal. In practice, we can never construct a system where the output will depend upon the future input values. Then the other property that we saw was invertibility. What does invertibility mean? It simply means that there is a one-to-one map or relationship between the input and output signal. So if we can uniquely identify what was the input signal just by knowing what the output signal was, then we claim that it is invertible. From the output, we can always go back and then say what the input was. Right? So such systems are called invertible systems. So if you want to check if a particular system is invertible or not, all you need to know is try to find two signals which produce the same output. If you can find such two signals which will produce the same output, then you can safely declare that the system is not invertible. So if you actually want to show a particular system is invertible, then you will have to find the inverse of the system itself, where the inverse system will take the output of the original system and should be able to produce the input itself. So that's how you show a particular system is invertible. Okay, the next property is stability. So stability simply means that when you give a bounded input, that is, the input magnitude or amplitude does not grow unbounded to infinity. So it is bounded. It is always within a finite limit. So when the input is bounded, the system should also be able to produce a bounded output. This is what we call as BIBO stability. So in that case, the system is said to be stable. If it produces an unbounded output even for a bounded input, then the system is unstable. So these are the basic fundamental properties of the systems. And then we saw some examples: the integrator, the differentiator, the amplifier, and the delay element, which is basically the time shifter. So we saw that these elements will have memory and they are all causal. And of course, both differentiator and integrator turns out to be an unstable system. The next set of systems that we saw was the LTI systems. So the LTI system is a special category of system which satisfy two specific properties, what are known as linearity and time invariance. What is linearity? It simply means that superposition property is satisfied. What is superposition? That if you have a signal x1 of t which produces an output y1 of t, another signal x2 of t which produces an output of y2 of t, then superposition says that you should be able to scale these two signals with any scalar constant, and if it produces a similarly scaled and added version of the output. Basically, you scale the inputs and superposition them together at the input of the system, then the output also similarly gets scaled and superpositioned together. So this is what is known as superposition property. If this property is satisfied, then we say that the particular system is linear. In other words, this input is a linear combination of multiple different signals. Then the output also turns out to be a linear combination of the corresponding outputs. This is linearity. Then what about time invariance? Time invariance simply says that the system configuration or the system property does not change with time. So if you delay the input by a particular amount, the output also gets delayed by the same amount. The system characteristic, the way it processes the input, does not change over time. Okay. In other words, the system characteristic or the system map is not a function of time. It is independent of time. So if you delay the input, if you delay the input signal by some amount, the output signal will also get delayed by the same amount. Okay, that's what time invariance means. And of course, we saw that all passive electric circuits and components like the capacitor, the resistor, inductor, all of them end up being LTA system. So this is very special to electronic engineers, because all the electronic circuits and electric circuits can always be modeled as an LTA system, and this helps in the analysis of all the circuits that we would be constructing. Okay. And when did we say that we will understand a system? We said we will understand a system if we know the input-output relationship for any possible input. And specifically for LTA systems, this can be characterized by what is known as the impulse response. So what is an impulse response? Impulse response of any system is very simple. The impulse response of any system is nothing but the output of the system when you feed an impulse, when you feed a Dirac delta as the input. That's all is the impulse response. But this impulse response becomes very special for LTA systems alone. Okay. And why is that? Because the output of an LTA system can always be expressed as the convolution of the input and the impulse response. And we can also tell a lot more about these LTA systems just by looking at its impulse response. For example, if the LTA system's impulse response is given to you, then you can look at it and then see if it has non-zero values for negative values of time. That is, if some impulse response is given to you, okay, let's say this is the impulse response. Typically, we denote the impulse response with h of t. And if the impulse response has non-zero values for negative values of time, then we know that because of convolution property, this signal will end up creating a non-causal output. For this reason, the LTA system is causal only if the impulse response is right-sided and exists only beyond time t equal to 0. Okay. So this is a very important observation that we can use to infer the causality of LTA systems. Now, other than causality, we can also comment about the stability of LTA systems just by looking at the impulse response. So we can take the impulse response and find its magnitude and just find the area under this entire magnitude signal. Okay. If this area is finite, that is, if the impulse response is absolutely integrable, then it will also so happen that the output will never grow unbounded when the input is bounded, which means BIBO stability can be guaranteed if the impulse response is absolutely integrable. Okay. Now, we said the important property of an LTA system is that you can completely characterize the system by knowing its impulse response, meaning for any possible input, you just find the output by convolving the input with the impulse response. Right. So this is the important property that we showed will exist for only LTA systems and not for any other kind of systems. So what is convolution? The convolution is simply nothing but if you want to convolve x of t with some h of t, what do? You take the signal x of t, multiply that with the time reversed version of h of t, okay, and then you don't simply just time reverse and multiply, but you time reverse and keep shifting this h of t. That is, if you want to find y of t, that is, you want to find the output's value at some particular time t, then what do? You time reverse the signal h of t, shift it by the amount t where you want to find the output. So if you want to find the output at 10 seconds, let's say, then you time reverse the impulse response and shift it by 10, then multiply that with the input and then compute the area of this product. So this is what we call as the weighted sum, right? So you weight the impulse response with the input, or you weight the input with the shifted impulse response. You can see it as both ways. So the output is nothing but the multiplication of the input and the shifted impulse response. This product is what we call as weighting, okay, this weighting, okay, and find the area at each and every time instant where you want to find the output. So this is what we refer to as convolution. and the convolution relationship helps us to find out the output of any LTI system. And this also gives us very nice observations and inferences that we can make from this observation. So what are those? So the first thing that we can notice is that if a system is invertible, let us say that we have a system whose impulse response is h of t, and there exists another system which is the inverse of this system which has an impulse response g of t. Then when you cascade these two, effectively what happens? You get the output of one system, feed it as the input to its inverse, which means its output should be the original input itself. In other words, the convolution of these two impulse responses should produce Dirac delta. This is a very nice observation that we can use to check if a particular system is an inverse or not. So if I give you two systems and give their impulse responses, and you can convolve with one another, and then if it so turns out that it is the Dirac delta that you get as the output, then you can say safely that one system is the inverse of the other. Convolution also satisfies some other interesting properties, namely commutativity, associativity and distributivity. So what are the use of these properties? The first thing that we saw was, because of commutativity and associativity, we can swap the order of systems. It does not really matter in which order you compute the output when two systems are cascaded, when two LTA systems are cascaded. So you can find out the output of the first system or the second system and then feed it as the input to the second or the first system. It does not really matter, the order does not. You can swap at any time in a cascade. Okay, that's the biggest advantage of commutativity and associativity. For example, let's say we had a sequence of systems like this. Let's say this is some h1 of t, and this is h2 of t, and this is h3 of t. Okay, and if somebody says find the output for some x of t, you can convolve this x of t with any of this h1, h2, h3 in any order. It does not really matter. It can so happen that if you convolve x of t with h2, it might be easier than convolving it with h1. So depending upon what is easier, you can do that convolution. It might so turn out, let's say if h1 and h3 are inverses, that is h3 of t convolved with h1 of t is equal to delta of t. If this is true, then our convolution becomes very simple, because then the total output would simply be x of t convolved with h2 of t. You need not even do this convolution with h1 and h3. So if somebody gives you a system like this and then it so turns out h1 and h3 are inverses, then it's actually simple. You just do this convolution. So you can simplify your system by knowing these properties. Okay. And the final thing that we saw was what is known as the unit step response. So what is unit step response? It is simply nothing but the integral of the impulse response. So you feed in a unit step to the input, then you observe its output. From that, can you comment what would be the impulse response? You can do that just by taking the derivative, because you can get the unit step function as the integral of the Dirac delta signal. And the other way around, the Dirac delta signal is simply nothing but the derivative of the unit step signal. For this reason, if you are feeding in the unit step input to a system, then the output of the system is as good as feeding in the impulse to this system and then integrating it. Because the order of cascading these two systems does not matter, you can put the integrator first, which will give u of t, which is essentially the first system that you actually wanted, right? One thing to note is that we said that integrator is not really a stable system, meaning the output of the integrator can grow unbounded. So it is very important to ensure that the input outputs that we are working with here, when we are working with unit step responses, they are all bounded, because if they grow unbounded, then you can have an output which is undefined or which goes to infinity. When it goes to infinity, then it may so happen that you cannot do this derivative operation and then claim that one is the input of the other. So remember, this commutation or swapping of the systems makes sense only when the output at each of the system is defined. It is not going to infinity. For example, you take the integrator, okay, and if you feed in a constant signal to this integrator, it produces an infinite output at the end of the system. So the output is always infinity. Then we will not be able to know what was the signal that was actually fed to this integrator. You can feed in 1 or you can feed in 10. For both you will get infinity as the output from this integrator. So the integrator is actually becoming unstable for certain inputs. So whenever you feed in these inputs, the integrator is unstable and you will not be able to invert back for these inputs. So for this reason, integrator becomes unstable and not invertible. But in many of these non-invertible systems, what we can do is, if we restrict ourselves to a small class of signals, then it is possible to invert back, okay. But in general, if there exist two signals where you feed in to the system and you see an output which is the same for two different inputs, then it is non-invertible, okay. This is the general definition of invertibility. Of course, whenever a system is non-invertible, we can focus ourselves to ensure that it works only on a certain small subset of signals. If you can restrict that, you can still have an invertible system out of a non-invertible system. And from our examples, one thing, if we observe, all the non-invertible systems also ended up being unstable systems. So that is an interesting observation, because whenever a system is unstable, it means that there exists an input for which the system grows in an unbounded fashion. So if there exists an input for which the system's output is undefined or is infinity, then you can scale that input by some amount and you will still get an undefined output or infinity. So for this reason, you have essentially found out two signals which will produce the same output, and hence it also becomes non-invertible. So most often it will happen that whenever the system is unstable, it is also not invertible. So this summarizes most of what we saw under systems, and we'll end this with a very important property of the LTI systems. The LTI systems have an interesting eigenfunction, and that eigenfunction is the complex sinusoids or the complex exponentials that we described in our signals. So we saw that complex exponentials are already eigenfunctions of the differentiators and integrators, and differentiators and integrators are LTI systems. But not only to these systems, but for any LTI system, the complex exponentials are eigenfunctions. That is because they are eigenfunctions of the convolution operation itself. Okay, we'll see this in detail and how this helps us. Because of this eigenfunction notion, we can simplify the convolution. We'll see that in the next lecture.